Howdy. I'd like to teach you today a proof technique called induction. This is a very, very powerful technique, and I want to use induction to prove the power rule for non-negative powers of n. The idea behind induction is that we have a statement, a true-false statement, P, and it's going to be true for some integers, and those integers are going to be all of the integers greater than some base case. For example, I might claim that the sum of all of the integers from 1 to n adds up to n times n plus 1 all over 2. Maybe this is true, maybe it's not, but I'd like to claim it and I'd like to prove it. So P of n is the entire statement right here, the equality. And the equality is either right or not. If it's right, then the statement is true. And if it's wrong, then the statement is false. So what I'd like to do is to prove that. But I need to decide what is the smallest integer that I want to make this claim for. So let's be reasonable about it and say that this statement is going to be considered true for all integers greater than or equal to 1. So that's our setup. The way induction is going to work to prove this is we're going to work in, we're going to take 2 steps. First of all, we're going to prove the base case. And the base case in our case is for n0 to be 1. And the way that we check the base case is to take this expression right here and just verify. When you plug in n equals 1, it works. And in this particular case, we're adding up all the numbers from 1 to, well, 1. So there you go. And that should be equal to, according to our expression here, 1 times 1 plus 1, or 2, all over 2. And wouldn't you know it, lo and behold, that works out. So we're going to prove the base case as our first step. Then, having proved the base case, we're going to prove that if P of n is true, then it implies that P of n plus 1 is true also. And the reason this is effective is that we already know that P of 1 is true. And so if we can establish that P of n implies P of n plus 1, then that really means that P of 1 implies P of 2. And if P of 2 is true, then that implies P of 3. And if P of 3 is true, that implies P of 4, and so on. In other words, I have proved the statement for all integers greater than or equal to 1. Now, how does it work? Well, let's examine what P of n and P of n plus 1 would look like. P of n is the statement that all of the integers, the sum of all of the integers up to n is equal to n times n plus 1 over 2. So P of n plus 1 is going to be that statement applied to n plus 1, that the sum of all the integers up to n plus 1 is equal to n plus 1 times n plus 1 plus 1 all over 2. In other words, I took and simply substituted in n plus 1 here, here, and here, everywhere where there was an n. And so what we're trying to show is that if Pn is true, then that will force Pn plus 1 to be true also. So let's see how that works. So we start off, suppose P of n. Now we're going to take the sum of all the numbers from 1 to n plus 1, and we're going to show that they have to add up to this expression right here. Equals. Now here's where we get our induction hypothesis. I am supposing that P of n is true. And P of n is the statement that the sum of numbers from 1 to n is n times n plus 1 over 2. So I'm going to replace the sum of numbers from 1 to n with what it is, which is n times n plus 1 over 2. And now I'm going to cleverly notice that I have a common factor of n plus 1. So we'll factor that out, leaving me with n over 2 in the first term and 1 in the second term. And I get a common denominator. And would you look at that? Just look at it. It's exactly what we needed to prove right here. In other words, if you allow me to assume P of n, then I can prove to you that P of n plus 1 is true as well. And that gets me from P of 1 to P of 2, because P of 1 is already true. And then that gets me from P of 2 to P of 3, and so on. So we have base case. We prove it for the smallest value of n that is allowed. And then we have the induction step, in which we prove that P of n implies P of n plus 1. So that's induction. Now, how do we use that to prove power rule? Well, it's actually kind of nice. Here's my claim, that the derivative with respect to x of x to the n is n times x to the n minus 1 power. And I'm going to claim that this is true for all integers greater than or equal to 1. I could actually make it work for greater than or equal to 0, but let's do greater than or equal to 1 because the x to the 0 case is a constant already, and we've already got a constant rule. So we begin with the base case. The derivative of x to the first, well, that's just the derivative of a linear function, and we already have a linear function rule that gives us that this derivative is equal to 1. Did that work out? Well, let's check. We have to check it against the claimed result to see if it works out. Is that equal to 1 times x to the 1 minus 1? And sure enough, it is. So we're happy with that. Our base case checks out. Now we go for the induction step. We're going to try to prove that P of n, here's our P of n, implies P of n plus 1. And if you need to explicitly construct P of n plus 1, that might be helpful. So here's P of n. And what we're trying to prove is P of n plus 1, which is found by replacing n with n plus 1 in every instance. So that would be the derivative of x to the n plus 1 equals n plus 1 times x to the n plus 1 minus 1. Just like that. So what I'm trying to show is that if you give me this, then that follows. So here we go. We're going to begin by taking the left-hand side, the derivative of x to the n plus 1, and we're going to try to rewrite it so that we can make use of our induction hypothesis. And what I observe is that x to the n plus 1 is the same as x times x to the n. And that's helpful to me because I have a derivative for x to the n, and I also have a product rule. And that lets me say that this is equal to x times the derivative of x to the n plus x to the n times the derivative of x. Now, using the induction hypothesis, we can say that this is equal to n times x to the n minus 1. And of course, using the base case, that's simply 1. Well, let's simplify a little bit, because x times x to the n minus 1 is simply x to the n. And now I have a common factor of x to the n, which can come out. And when I do, I get n plus 1 times x to the n, which is mathematically equal to the p of n plus 1 that we needed. Well, here it is. If my power rule is true for n equals 1, then it has to be true for n equals 2. And if true for n equals 2, then it has to be true for n equals 3, and so on. That's kind of it. I want to extend this just a little bit and consider we have a power rule for n's greater than or equal to 1 for integers. Well, what about the case where n is equal to 0? Well, then that's true also because of the constant rule. So the derivative of x to the 0 should be 0x to the minus 1, which is equal to 0. And that's equal, and so that's correct because x to the 0 is a constant. What about for n less than 0 in integers? Well, I think we can do that, but I think we're going to have to do it by appealing to quotient rule. We can say that the derivative of x to the n, where n is negative, is the same as the derivative of 1 over x to the negative n. And now if we appeal to the quotient rule, this gives us low d high minus high d low. Now, the d low is going to be a little bit tricky because negative n is a positive number because n is less than 0. And so I can use the power rule on x to the negative n. Now this cleans up really nicely because this whole term is 0 and my negatives cancel here, giving me n times x to the negative n minus 1 all over x to the negative 2n. And as we know, dividing x2 powers gives me subtraction of exponents, so that I get n times x to the negative n minus 1 minus negative 2n, which is the same as x to the n minus 1. So lo and behold, when n is less than 0, then the power rule holds as well. The upshot of this is that we have covered all possible cases. We've covered positive n, 0, and negative n, so that if n is an integer, the power rule holds. Obviously, there's some more territory. We have to consider fractional exponents.